Seems that we have already some attendees this excellent seminar. At this stage, I would like to welcome you all in the name of Battery 2040 Plus initiative, and especially in the name of Christina Enstrom, coordinator of this initiative, who cannot attend this meeting today or this seminar today. My name is Robert Dominko. I'm from National Institute of Chemistry in Ljubljana, Slovenia, and I will make a short introduction to the excellence seminar, who will be given by Professor Dr. Maximilian Fichtner from Helmholtz Institute in Ulm, Germany. And after that, after his presentation, we will have a Q&A section. So if you have any questions, you can raise them already during the lecture, but all the questions will be answered at the end of the lecture. So Professor Max Fichtner works at Helmholtz Institute of Ulm, and as you will see later, he has also many other affiliations. And one of his duty is also, he is heavily involved in Battery 2040 Plus initiative, which is large-scale research initiative aimed to invent the sustainable batteries of the future. So the idea is to work on different pillars and to provide different research directions, and with that to enable long-term European leadership in different markets. So with this aim to provide different research direction, Professor Fichtner is a work package leader of ambitious work package where we are creating a roadmap, which is basis for the different projects that are then financed under umbrella of Battery 2040 Plus initiative. At the beginning of this initiative, we have designed three major directions. Those are accelerated discovery of battery interfaces and materials, so-called Big Map. And then the second pillar is integration of smart functionalities, including sensors and smart scaling functionalities. And the last pillar is cross-cutting areas, including manufacturability and recyclability. So as I said, Max and his team are leading this work package, and with all other partners that are members of the core group, and also the other partners which are not members of the core group, we are creating the roadmap that is then basis for the future projects. This roadmap is chemistry neutral, and it enables to tackle different chemistries. And today we are going to hear from Professor Fichtner the lecture entitled Energy Storage Beyond the Lithium, where I presume he will mainly tackle multivalent metals like magnesium, calcium, perhaps also aluminum. Why those three metals? If you just check, those three metals are highly abundant in the Earth crust. They are very well distributed over the world. So there is almost that actually enables a sustainable approach, and also that enables electrification using batteries in much higher extent. Besides that, those three metals are also interesting through their energy density, especially volumetric energy density of metal anode, which can be applied into the novel type of the batteries. But there is a still long journey, and we need to bring a lot of puzzles together from anode, from electrolyte, from cathode sides. All of them are touched by the work of Professor Fichtner. And with that, actually, at least according to calculations and according to some pre-existing prototypes, we can afford or we can build cells which energy density will be comparable, at least comparable to the today's lithium-ion batteries. And of course, with that, we will be in position to place batteries in much larger extent that we are planning today with lithium-ion batteries. However, why we don't have this today? Some of research can be already mature. Some of it's fresh, and where Professor Fichtner has also significant contribution. For example, calcium batteries, and some of research is ongoing, but is somehow stuck with the chemistry around ionic liquids that accounts for aluminum plating and stripping. Whereas other two actually cases are much more advanced, and they go in. They can be shown, or they can be resulted in different electrolyte solutions, and also compared coupled with different cathode materials and anode materials. With that, I hope I introduced you a little bit what we are going to hear in next 45-50 minutes. And I leave the stage to you, Professor Fichtner.
Thank you very much, Robert, for this very kind introduction. So I'm going to share my slides. That should work. Okay, I hope you can see it.
Everything is fine.
Okay, then let's start. So it's a great pleasure to introduce an activity which is actually an activity between various sites. It's a joint activity of Ulm University, of the Karlsruhe Institute of Technology, with contributions from the Center for Solar Energy and Hydrogen Research in Ulm, ZSW, and the Justus Liebig University in Gießen, the group of Professor Janek. So it's about the structure and some work within the cluster of excellence, energy storage beyond lithium. We abbreviated it as POLiS, post-lithium storage. Actually, the entire activity basically goes back to the late 2000s, when the two sites, Karlsruhe and Ulm, basically recognized that they nicely complement each other from their activity spectrum, from their competencies. So while in Ulm we always had a strong activity on fundamental electrochemistry and modeling, etc. In Karlsruhe, there were strong engineering activities, or are strong engineering activities, and materials research activities. Yeah? And then we have in Ulm also the more industrial-oriented ZSW, also with materials research activities. So there's an entire spectrum where the things can complement each other. And the first visible sign of this wish to combine these forces was the foundation of the Helmholtz Institute Ulm. So this is my home institute. That was founded in 2011 as a future, or to become an excellence, a center of excellence in battery research in Germany. And meanwhile, we have about 150 researchers at the institute who work on various topics, a mixture of lithium-ion and post-lithium activities. And the founding institutions of these institutes are Ulm University, the KIT, but with associated partners, the ZSW, and the German Aerospace Center, which runs an entire modeling department at our institute. Okay. The next activity in that respect was actually that we wanted to strengthen these links between Karlsruhe and Ulm. And one opportunity was that we participated in the recent round for excellence clusters. in Germany. Excellence clusters are a strategic funding instrument of the German research foundations. German is Exzellenzstrategie, and the purpose is actually to strengthen already strong and visible activities at universities in Germany, with a very strong commitment to a science-driven process. So this is less application-oriented, it's more fundamental or research-oriented. No? So there can be applications by single universities or joint applications. In that case, it were 3 universities, Ulm University, KIT as main partners, with University of Gießen as an additional associated partner. So, and eventually there was money almost for 57 clusters in Germany, and we wrote a proposal. Our idea was to suggest an activity which is about energy storage beyond lithium, and among these 5 or 6 proposals that were submitted on the battery research, this was the only one which survived in Germany. Eventually, we won this activity, and we are funded now for 7 years, which is pretty good, I have to say, by 47 million euros. And this is basically money so that you can employ 110 to 120 people. Even more if you take visitors, etc., to it. So this is a pretty strong and visible activity. Yeah. Okay, as Robert already pointed out, there is a strong motivation to go in that direction. One is, of course, to switch to more sustainable systems, but as you can see in this diagram here, there's also the opportunity to improve the properties of systems, but especially the volumetric energy density can be higher in principle because you can use metallic anodes, as you can see it here. And here on the left, these are the ions which we have on our list, which we are studying at the moment. So you can see this is not only monovalent and bivalent, there's also trivalent, and there's even a negative shuttle, the chloride ion battery, which is also a possible system. And we also took that because we had the first paper and basic patent on that. So we wanted to explore the possibilities to go in that direction. Okay, with all that in mind, we have strong ambitions. We have high ambitions. We want to lay a foundation for new electrochemical energy storage systems which have the potential to overcome the limitations of the current battery technology. And therefore, we need to work on many different topics. So we need new anode materials, we need new cathode materials, electrolytes, but also new engineering concepts. And this is all done with the research in mind. So these are all research projects, not application projects. Yeah, and this involves a series of activities, and you need to bundle the competences that are available. We need fundamental electrochemistry studies on surfaces. We need to understand what is happening when a liquid gets in contact with a solid. We need to find new ways to synthesize the electrode materials. We need to analyze these systems. We want to also push the toolbox of analytical methods to a little bit further and add new ways to study these systems. Modeling is, of course, a very strong tool that we are using. processing and fabrication is on our list, and we do safety and sustainability studies. Yeah, and on the way of actually all of these systems, we are addressing, or we are envisaging these major roadblocks that we all have in front or ahead of us, and which we have to overcome in order to be successful. So one is the low ionic mobility in solids and liquids. This is especially true for the multivalent systems. And then the interfaces are really a critical point, because often you have a system that seems to be able to work, but it doesn't work because there is some interface issue somewhere. So this is a very important point also to design, not only to understand, but also to design such interfaces. The degradation is the reason why the lifetime of these systems is limited. We need to understand what's going on in the electrolyte and also the active materials when the stuff is cycled. And we want to understand why some charge and discharge processes are not so well reversible and limit our cycle life. This entire activity had to be structured. And we wanted to have a benefit from the number of different competencies that we had in the consortium. So we wanted to bundle them in various pillars, and these are the so-called research units. One research unit is electrode materials. We have an electrolyte research unit, interfaces. Then we have a more technological oriented research unit. This is integration, sustainable cell engineering. And then there are cross-sectional topics like modeling so-called descriptors. I will give an example for that, but also some other research topics. Yeah, and across all these activities, we have our competencies which diffuse into the necessities that pop up in every of these, in each of these research units. When we started, we were actually quite lucky that at least in Ulm, we could get a new building where we could move into. This is in the Lise-Meitner Street, number 16. This was an industrial building, which is relatively new and sold to the university. And there we have more than 1,000 square meters of physics and chemistry labs, where 2/3 have already been opened in 2021. And this is a very nice building. Here's a view from the coffee room, where we also can have meetings. And the laboratories are already running. Here's a view on the materials acceleration platform from Helge Stein. You see here the ambient pressure XPS on one side, and here's a row of glove boxes where they develop these autonomous robot line. This is a view in the chemistry lab, and here in the physics lab. So basically everything is running. That took a while, but now we are really happy that it works. Okay, so after the first 3 years where we are now, we have almost approached half-time. There have been some results where we think this has already been a remarkable contribution, like first well-working room temperature electrolyte for calcium batteries. We have just a paper under review where we show a calcium battery with a cycle life of 5,000 cycles. We have pretty fast magnesium systems and so forth. I don't want to go to every detail. I will select some of these topics and will show some results on that, on monovalent, but also bivalent systems. So, and here are these examples that I mentioned. I will say a few words about layered single crystal cathodes for sodium-ion batteries. So I think you know that sodium-ion batteries have become a pretty hot topic recently. Then I will say something about the ionic mobility and the storage capacity in multivalent batteries, what we have done there, about overpotentials in magnesium batteries, but also calcium batteries. This is a really big roadblock, I have to say. And then one example from our cross-cutting activities about so-called descriptors. So let's start. What we have been addressing in one of our projects is a system of a cathode material for sodium-ion batteries, where we leave out, I would say, every critical or expensive or toxic transition metal. So we want to use a cathode material which is entirely based on manganese and magnesium. So it's a layered system. And this system is known to suffer from a lot of things. It is not stable in air, so it cannot be processed in water. It degrades quite quickly. And the question is, what can you do here? What all the activities in the past did is that they actually produced a very fine-grained polycrystalline material. And our idea was, or the idea of Venkat Pamidi, who did this work, was actually to benefit from the work that has been done in the lithium-ion battery field. Jeff Dahn, Tesla, etc. They have moved to a more single crystal concept of their materials because they have better stabilities. And this is exactly what was done here. So you see here two electron micrographs here with a polycrystalline system that was heated to 900 degrees centigrade. And here you see a crystal that was heated to 1100 degrees. And then you really get a homogeneous crystal here. You see that also in the SAED pattern, which confirms actually that you have a single crystal nature. And these materials are pretty stable. You can leave them in air, in humid air here. After 30 days, you find that the polycrystalline material reacts with the humidity in air. It forms, even in the XRD, you see additional phases like the Bernouside here. And this is not visible with the single crystal material. So this is more chemically stable, but it's also performing better. Yeah, you see here quite large differences in the capacity of these materials depending on the temperature treatment here. And also here are differences at different rates, which gets smaller and smaller the higher the rate is. And then eventually at pretty high rates, 5C, the whole thing turns around. And this is where we think the fact that you have a large crystal and you have long diffusion distances takes its toll. Yeah, and this is probably the reason why these materials at high rates fall behind the polycrystalline ones. Yeah. Another positive aspect is that if you heat these materials to elevated temperatures, more than 300 degrees, you see here in these DSC trays, there's a strong exothermic peak here, exothermic event of the polycrystalline system, which obviously releases heat when it relaxes to a single crystal state. And this is much lower in the case of the single crystal system. So this is more stable and also more safe in that respect. So if you want to summarize the outcome of this activity, you see that a single crystal is actually improving the properties, all properties except for the rate capability at higher rates. I said that this turns around, but every other aspect looks better than, I would say, the classical material. An activity which was related to that was the development of new binders, because binders can play an essential role in the performance of batteries. And what we did here was to develop multifunctional aqueous binders for sodium-ion batteries. Multifunctional in that they do not only bind the materials, do not only glue them together, they also have a certain sodium-ion conductivity. So if they are binding the materials, still the sodium can enter or can be taken up from all the different facets of a crystal. And this is something which pays out. Eventually, we took here the same material than before. And here you see the results of such a study. The only the only organic binder here was the PVDF. This is our benchmark, if you will. This is the standard binder. And all the others here are phosphates, metaphosphates, and silicates. And you basically see that there is a much better performance after some cycling when the inorganic binder is used. You see here, the black line here is the this is for NVP. Black line is for the PVDF, and the others here are here. This is a metaphosphate here. Sodium trimetaphosphate is performing much better, and you see a considerable difference here. Also, the safety is better. You see here again. This is the electrode prepared with PVDF. As a binder, and this is the electrode prepared with the inorganic binders, so you do not see a strong exothermic trace here. Eventually, a couple of things improved, the processability, but also the capacity retention was improved, especially here of this layered system, which is a little bit a critical thing because this is prone to degradation. Here it's more stable, but also here you see an improvement when you take this particular binder, and also the mechanical properties are quite good. This can lead to a flexible coating, and you can even roll it, and so everything remains stable and nothing is detached. And here are also related results. We have here a polycrystalline manganese nickel oxide with various binders. Yeah, so here the green one is the PVDF, the other ones are CMC and the phosphate binder. And here we have a comparison of single crystal and polycrystalline material. And this is the charge and discharge curve related to that. Okay, so let's jump to the multivalent batteries. And there we'll say a few words about our electrolytes, a new storage concept, if you will, and something about overpotentials. So what we came up with a while ago was a discovery of an electrolyte which actually goes back to very early concepts. So we wanted to have a salt-like electrolyte, not these complicated reaction systems like the Schlenk equilibrium that we had with our previous magnesium electrolytes, for example, where you can expect many side reactions and a quite complex behavior. We wanted to come up with a salt where you have the cation and an anion and everything remains stable and the cation is moving around. Yeah, and this is basically possible if you make the anion, if you design the anion such that it is pretty large and it's not coordinating well to the cation. If you achieve that, then the cation is well mobile and everything is stable. And so what we did here is that it's a very, very simple reaction. You take calcium, for calcium electrolyte, you take calcium borohydride. This is something you can buy from Sigma Aldrich. And you let it react with fluorinated isopropanol. This is another commercial compound. So you let it drop inside. You have DME as a solvent, make a reflux. What you get is the product. Yeah, so this is the calcium salt. The borohydride reacts with the acidic proton here of the isopropanol. And the only byproduct is hydrogen, which goes off. Yeah, so you get basically full conversion to the product. You don't need to make complicated intermediate steps. Also, you make the reaction, and then you get this electrolyte. And this is a single crystal image from the product that you get. You see here the calcium. This is coordinated by solvent molecules, DME in that case. And here you have this hexafluoroisopropanolate boro complex. Yeah, so this is the boron with 4 of these isopropanolate complexes. So this looks a little bit like a hedgehog, where you have the fluorines outside, and they don't want to get in contact with anything. They leave the magnesium or the calcium alone here. And the properties are quite amazing, I have to say. So it strips and plates very well here. The stability is very good. It's around 4 volts or higher, depending on how you make it. It's 4.5 volt here. The ionic conductivity is comparable to that of lithium electrolytes. So we have measured 8 to 11 millisiemens per centimeter. So you get a high rate capability. And this allows you also to work with high voltage cathodes in case you have one. Yeah. And as already mentioned, this is a quite easy and quantitative synthesis from commercial compounds. Okay, and maybe not to forget, we also did some calcium sulfur studies a while ago. So these were the first results here. You see, as always, the decay of the capacity, but this comes from the cathode, from the polysulfides. Okay, then another challenge, and everybody knows that who's working in this field with multi-valent systems. A grand challenge is the ionic mobility of these ions. And this is something which heavily affects the storage capacity of multivalent batteries. Here you have some examples, and the people who did modeling in this field came out with energy barriers for the hopping of these ions in the material, which are quite high and mostly unacceptable. Yeah, so you won't end up with a well-working system if you have energy barriers which are beyond 500-600 milli-eV. So this is leading to nothing. So, and if you look what was done in the literature in the field, most people were actually pursuing conventional strategies, in that they tried to test analogons of lithium and sodium systems, like layered oxides, polyanions, spinel structures, open framework structures, etc., and wanted to solve the problem by crystal regulation strategies. Yeah. But as an outcome, we are still looking for good insertion type materials in this field. So there's still a lack of suitable host structures for divalent ions. So what can you do? Now, as it came out, it was suspected a while ago already, is that not only the structure rules here, it's also the electronic structure that can have an influence. And in fact, if you think about a system where do not have this strong interaction of the cation with here the polyhedron, where it's interacting and you have this very strong polarization. If you rather go for another system where the interaction is weaker, yeah, in the past this was called soft anions or whatsoever, where you have less polarization, yeah, then this may work. And this is basically possible by involving both the electrons from the cations and the anions. Yeah, if you manage to get a delocalization of both, then you may achieve a redox reaction where not only the cations but also the anions contribute, and this is reversible and leads to a higher storage capacity. And this is an example of one of our model compounds that we have, where we had actually discovered this. And this is a case where the transition metal 3D electron band interacts with the sulfur 3p band, yeah, so that you get a delocalization of these orbitals, and you get a better access of the electrons by these means. This was discovered by Chen-Yu Li here at the INT, and he called this system or this principle SCAR, simultaneous cathode and anode redox. And the first compound where this was studied was the vanadium tetrasulfide. Yeah. This is a natural mineral called petronite. Yeah. And with this material, you could achieve actually storage of more than 1 electron per magnesium atom. In that case, it was 1.3 roughly. Yeah? And this also enabled him to achieve specific energies beyond 300 watt-hours per kilogram. Yeah? And in this diagram here, you also see that the comparison looks quite good if you compare it to other systems. Here on the right, you have a charge and discharge diagram. Okay, that this doesn't only work with magnesium, but also with calcium is shown here. Yeah? We have this aforementioned calcium electrolyte with the hexafluoroisopropanoate, the boron complex. We have calcium metal as an anode. We have VS4 as a cathode. Yeah? And this is what you get here on the left. The structure of this VS4 is quite interesting. So this is actually consisting of strands or chains of VS groups here. This blue is the vanadium, as is the sulfur is yellow. Here you have this bridged systems. And if you look from the side, you see that there's also space, and this is good for the movement. So you can imagine, this is maybe also the reason why this material is extremely fast. You can imagine that you have like race cars, these are our calcium or magnesium ions. They are rushing through these tunnels here, and here on the side you have the strands of the VS4, and then they can dock, can stop, and can either release some charge or they get some charge, and then they go on. Yeah, so this is a nice picture for what is going on there, and this is possible because you get this delocalization. Okay, next point is over potentials, and as we all know, these multivalent anodes, they tend to passivate. If there's the slightest amount of water in your electrolyte, your anode stays passive and doesn't want to start working. Yeah. What is also known, or what came out from various sites recently, was that alloys may work much better, yeah, in that respect, and that there's a less build-up of blocking layers, and there are the kinetic barriers which are much lower than with the pure metals. But if you don't want to have your entire anode consisting of an overwhelming part of non-active alloy species, and only a part of it is magnesium or calcium, you can also solve that problem by establishing a thin layer on the top, and that was done in this work. So what was done here by Chen Meng was that a magnesium bismuth interface was created just by adding a tiny amount of a bismuth triflate solution, 10 millimole. And this reduces and forms a bismuth layer at the surface, and the result here in the very first cycle is remarkable, I would say. Yeah, so there's a big difference. This continues. You see it here in the impedance spectrum, that there's a factor of 10 where this barrier is reduced, and this is even more pronounced when you go to higher rates. That this is not only possible by this bismuth, but also by other compounds is shown here. What was done here is that another additive, magnesium borohydride, was added in a tiny amount, and this forms a particular, can call it SEI layer here, which enables the magnesium to work from the very first cycle on. Yeah. We haven't quite fully understood what happens here. I mean, it's obvious that the borohydride has a strong reductive capability, and maybe the surface gets reduced. We do not get a really clear evidence from XPS, so this needs certainly further work, further studies in order to better understand that. But I would say the phenomenological effect, this is quite clear and convincing. Okay, last chapter is descriptors. So you may wonder, what is a descriptor and why we are doing that? Now, a descriptor is something which is actually just a number, and with this number we describe a very complex situation. Some of you may have some background from catalysis or so, and you may have heard from the volcano curve, which actually shows that the catalytic activity in the oxygen reduction can be very nicely described just by the oxygen binding energy at the surface. That means, although this is a very complex mechanism, it can be described correctly by one parameter only. This is a descriptor. And some other people may remember from chemical engineering lessons or so, there are dimensionless numbers like the Reynolds number or the Nusselt number. Reynolds number describes the laminar flow transition to the turbulence transition, etc. So very simple and correctly describing the situation, but there's something behind that, yeah? And you need to work out the proper relationships. Yeah? For us, this is something which we put on our list, because in our excellence cluster, we have the unique opportunity to benefit from all this work on the different systems, from the monovalent systems, bivalent, trivalent, even anionic systems. We can put all these data together, and we are still within the cluster and can use that, yeah, and can develop that. But you can also, of course, develop such a descriptor by plain thinking, and I will show you one example from that. Why are we doing this? We are doing this because the determination of descriptors can considerably speed up the research for novel materials with desired functionalities or multifunctional properties, because you just need one or two parameters to describe the properties that you can expect from this system. This is very helpful. Yeah, and as I said, such descriptors can either be identified rationally or based on a statistical analysis of functional materials properties. So this is, I would say, this is a vision that we have, that from all our collected data, we can identify such descriptors. Okay, yeah, the intellectual challenge now is to rationalize the physical and chemical principles that are underlying the presence of descriptors. Yeah? And here's just one example. This is, I would say, the first part of this descriptor study, which deals with the mechanism of magnesium transport in spinel chalcogenides. Yeah? As we have heard, and or as we know, the ionic mobility is a critical parameter in such systems. And what was found by Axel Groß and Mosen Sotoday in their theoretical study was that there's a preference of magnesium ions in tetrahedral and octahedral holes, depending on the so-called anion parameter. Yeah, and this is a parameter which is influenced by the lattice constant and the binding length in the different environments. And this is something you see here. This is K64. This is a ratio of binding length in octahedral and tetrahedral hole, where an ion would have to go through when it migrates. Yeah, and this interplay between the coordination and the bond length, this governs the magnesium site preference in spinel compounds, and it leads to the conclusion, this is what an outcome of their study was, that the interaction cannot be purely ionic. Now, this is not necessarily new. That there are influences from the anions and that there are soft anions, hard ions, which can influence the migration was known before, but it has not been really quantified in terms of a descriptor. So the calculations in that case also suggest that anionic redox plays a more important role in sulfide and selenide spinels than in oxide spinels. Also, this is not very surprising. But if we go to the next slide, we see that you can very easily and nicely describe the mobility in such a system by a thing which we called, or which Axel called, the migration number. Yeah, and this migration number is just a very simple equation where you have the radii of the anion and the cation. Yeah, you have the oxidation numbers of cation and anion, and this is U, if you will, you have just the difference of the electronegativities squared. Yeah, and the difference of the electronegativities has intrinsically also some relation between ionic and non-ionic binding situation in it. And you get a surprisingly good correlation, as you can see here. And these correlations here, they allow to predict the ionic mobility in new materials. Because you have very simple input parameters. You have the radii, you have the oxidation numbers, and you have the difference in the electronegativities. Yeah? And what they did is they applied that to various systems with various metal groups here, scandium, manganese, titanium, iron, and so forth. And it works in every case. And you can also take different ions and let them migrate through. The correlation remains linear. Yeah? And recently, this has also been verified by a machine learning method called SISSO. Don't ask me what that is. But this is something which can assist also to identify future compositions or compounds in that area. Okay, that's it basically. I would like to thank several people here in the order of appearance in this talk who contributed to what I showed, which is only, of course, a very small fraction of what has been done in the cluster. Many of these examples were from my group, because otherwise I could not give you an answer on your questions. And this is a picture where it seems that almost everybody is smiling. It was from our last conclave meeting in summer last year, where we met with our external advisors also. And that was, of course, an online event. But this year we are planning the first in-person meeting in our new building in Ulm, where we can have 120 people really in a big room and can meet and can talk and can discuss again. So with that, I invite you to visit our webpage, postlithiumstorage.org. And I thank you all for joining. And if you would like to see some more, go to one of these other websites. This is my institute, the Helmholtz Institute. This is the website, and this is the website of Celeste. This is this joint platform of Ulm and Karlsruhe for electrochemical energy storage. Thank you very much for your kind interest.
Thank you, Max. Thank you a lot for this inspiring presentation. And we already have two questions. One appeared during your lecture, and it is related to the calcium electrolyte, where you showed your example on using this hexafluoroisopropyl salt. So the question is, does the novel calcium electrolyte really plate calcium? If so, at what current density in terms of milliamps per square centimeter?
Yeah, number one, it does. It is, I have to say, it is not easy to plate calcium. And calcium is a tricky candidate. You cannot get it as thin foils. Yeah, this is a very brittle material. You have to make maybe a pellet a little out of it. And when you then strip and plate it, I mean, you can investigate it by XRD, then you see that it is really calcium. If you strip and plate it, you will find that in contrast to magnesium, where you get maybe a mirror-like plating, a shiny surface. In the case of calcium, you get some black mass on it, which can also be scratched away. And if you look through the microscope, there are many, many particles which seem to have a substructure on their surface. Otherwise, they wouldn't be black. So calcium is a tricky candidate, but it can be stripped and plated at I cannot tell any maximum numbers, but I think Chirong is in the audience. If you like, write it in the chat and give a number of the densities that have been used. No. I mean, when we tested it with the vanadium tetrasulfide, the rates were comparably high that we used.
Okay, thank you. We are moving to the second question, which appeared by the end of your lecture. And I think it is connected with the last part of your lecture. For the scaling relation, how is really the simple radius actually determined? For sure, it is also a function of the coordination number.
I didn't do this work, yeah. So for the final answer, we would have to ask Axel Groß. But I would expect that the coordination number has been taken into account, because otherwise this wouldn't make sense. You cannot just take some scale, irrespective of whether this is a tetrahedral or octahedral arrangement. So my educated guess is it was taken into account, but for final evidence, we would have to go through the paper, or ask Axel directly.
Yeah, thank you. We have one more question, and for all of you that you are still with us, please, if you have any question, just use Q&A section. So